The insane evolution of artificial intelligence. Opening Shockwave. Right now, as you watch this, artificial intelligence is crossing a line that humanity has never seen before. For most of history, our tools extended the body. Then they extended memory. Then they extended communication. But the new generation of AI is beginning to extend something even more fundamental, the act of thinking itself. For decades, computers were powerful but narrow. They could calculate, sort, retrieve, compress, and automate, yet they could not navigate ambiguity the way people do. They did not improvise gracefully. They did not explain ideas with fluency. They did not look at a messy problem and decide what mattered. Then, within what felt like a single compressed moment of history, machines began writing coherent essays, generating images from language, summarizing legal documents, drafting software, solving harder reasoning tasks, helping biologists predict protein structures, proposing scientific hypotheses, browsing the web, and even operating digital tools with limited autonomy. That is why this moment feels both thrilling and disorienting. We are no longer watching software merely become more efficient. We are watching software become more cognitively general. And once a technology starts improving across many domains at the same time, it stops behaving like a single invention and starts behaving like infrastructure. It changes not one industry, but the conditions under which every industry operates. What electricity did for machines, and what the internet did for information, advanced AI may do for cognition. That sounds dramatic, but the evidence is no longer confined to speculation. The transformer architecture introduced in 2017 replaced recurrence with attention and proved more parallelizable and more effective on major translation tasks. GPT-3 in 2020 showed that scaling large language models could dramatically improve few-shot performance across many tasks. ChatGPT, released in November 2022, turned those capabilities into a simple conversational interface that the public could actually feel. By July 2025, OpenAI reported that ChatGPT was being used weekly by more than 700 million users, sending more than 2.5 billion messages per day. At roughly the same time, frontier labs were no longer talking only about chat. They were talking about reasoning, autonomy, tool use, scientific collaboration, robotics, and safety frameworks for capabilities that could create severe harm if deployed carelessly. In other words, the conversation changed from what can AI say to what can AI do. And that changes everything. So this video is not about one viral product, one company, or one benchmark. It is about the arc underneath all of them. How did artificial intelligence evolve from a fragile academic ambition into a family of systems that can increasingly operate across language, vision, action, and science? Why did that evolution take so long to arrive and then seem to accelerate all at once? And why does it increasingly feel as if the technology is moving faster than the institutions that are supposed to govern it? Because if this really is the insane evolution of artificial intelligence, the most important part of the story is not that the systems are getting better. It is that civilization may still be organized for an earlier version of the world. The old assumption was that machines would master one narrow domain at a time and leave the rest of human cognition untouched for generations. Now the pattern looks different. Capabilities discovered in one domain spill into others, and each new interface puts those capabilities into more hands. When a model can read, write, see, search, plan, and act inside the same loop, progress stops feeling linear. It begins to feel cumulative, recursive, and frighteningly hard to slow. The long winter before the fire. To understand why the present feels so shocking, you have to remember how long artificial intelligence spent disappointing people. The term itself was formalized in the proposal for the Dartmouth Summer Research Project on Artificial Intelligence, drafted in 1955 for the 1956 workshop that helped define the field. The ambition from the start was enormous. Intelligence was treated not as mystical essence, but as something that might be described, analyzed, and eventually reproduced in a machine. That founding belief was bold, elegant, and also dangerously premature. Early researchers often assumed that once the right symbolic rules were written, genuine machine intelligence would not be far away. But reality was harsher. The world is not a chessboard of clean abstractions. It is noisy, high-dimensional, ambiguous, and filled with edge cases. Human beings do not merely apply rules. We absorb context, learn from incomplete data, switch frames, use intuition, and recover from uncertainty. For decades, computers could dominate only where the environment was tightly defined. That is why so many early AI victories were simultaneously impressive and misleading. They revealed real progress, but also hid how brittle the systems remained outside their sandbox. IBM's Deep Blue became a landmark in 1997 when it defeated Garry Kasparov, the reigning world chess champion, in a match under standard tournament conditions. That moment felt like a machine crossing into elite human territory. But Deep Blue was not a general mind. It was a specialized triumph built for an exquisitely structured domain. It could not explain biology, summarize a novel, or help a child learn algebra. It could only play chess at a superhuman level. And that pattern repeated over and over. Every time a machine conquered one benchmark, people understandably imagined that broader intelligence must be close. Then the limits would appear. Systems that looked magical in demos collapsed in messy reality. Funding cooled. Expectations crashed. Progress continued quietly, but public imagination moved on. What the field lacked was not intelligence in the abstract. It lacked the ingredients that make flexible learning possible at scale: enough data, enough compute, the right architectures, and practical ways to train systems on the complexity of the real world. In hindsight, one of the most important lessons from the early decades is that intelligence is not a single trick. It is an ecology of capabilities. Perception, memory, abstraction, planning, language, adaptation, and feedback all have to work together. Until that ecology began to emerge, AI would remain a sequence of dazzling islands rather than a connected continent. So by the early 21st century, many people still believed that truly general machine intelligence was either centuries away or fundamentally impossible. And that skepticism was not foolish. It was a rational response to decades of overpromise. What almost nobody grasped was that the missing pieces were finally beginning to align. The data was coming. The compute was exploding. The internet had become a training ground for language and images. Graphics processors were making large-scale neural computation affordable. And once those ingredients met the right learning systems, the field would stop inching forward and start compounding. The old era of AI was often obsessed with proving that a machine could mimic one visible surface of intelligence. Beat a champion. Solve a puzzle. Follow a grammar. Recognize a pattern. But the new era would be different because it would not begin from handwritten competence. It would begin from learned representations drawn from vast amounts of experience. That shift, from programming the world directly to letting models absorb structure from data, is the bridge between the age of symbolic promises and the age of statistical power. And once that bridge was crossed, the history of AI stopped being mostly philosophical. It became industrial. The dream did not return because researchers became more optimistic. It returned because the machines finally had a path to learn from reality at the scale reality demands. Deep learning ignition. The ignition point is usually traced to 2012. That was the year Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton showed that a deep convolutional neural network could dominate the ImageNet visual recognition challenge on a scale that forced the field to pay attention. The model, now known as AlexNet, was trained on roughly 1.2 million high-resolution images across 1,000 classes, and it achieved dramatically lower error rates than previous methods. To an outsider, that could sound like a narrow competition result. Inside machine learning, it felt like the ground shifting under everyone's feet. It suggested that if you had enough data, enough compute, and enough depth, neural networks could learn representations that older handcrafted pipelines struggled to match. That mattered not just for image recognition, but for the broader philosophy of AI. It implied that intelligence might emerge less from carefully encoded human rules and more from large-scale optimization over experience. After that, the progress was no longer isolated. It began to spread across domains. In 2016, DeepMind's AlphaGo combined deep neural networks with tree search and defeated a human European champion, while the Nature paper reported a 99.8% winning rate against other Go programs. For many observers, the real significance was not the game itself. Go had long been seen as a domain requiring intuition and pattern judgment beyond brute force search alone. When AlphaGo succeeded, it signaled that learned systems could capture forms of strategy that once looked deeply human. Then came the architecture that changed almost everything else. In 2017, the paper Attention is All You Need introduced the Transformer, an architecture based solely on attention mechanisms, dispensing with recurrence and convolutions in the core sequence model. The Transformer was not just another model. It was a scaling machine. Because it parallelized efficiently and handled long-range relationships in data so well, it became the foundation for modern large language models and, eventually, for many multimodal systems too. Once that architecture arrived, the field found a design that could drink from the fire hose of the internet. In 2020, GPT-3 showed what happened when you pushed the scale of language modeling dramatically further. The paper described a 175 billion parameter autoregressive model and showed that larger models could become far better at task-agnostic few-shot performance across a wide range of benchmarks. This was a crucial conceptual break. The old model of AI required building a system for each task. The new model suggested that one sufficiently large and well-trained system could perform many tasks simply by being prompted well. Then the boundaries between modalities started to blur. OpenAI's clip showed in 2021 that models could learn visual representations from natural language supervision using 400 million image-text pairs collected from the internet, enabling strong zero-shot transfer across many visual tasks. That result mattered because it hinted at a more general recipe: train on massive cross-modal data, and the model starts to build reusable concepts rather than brittle labels. Language was no longer separate from vision. Vision was no longer separate from reasoning. The system was beginning to form a more unified internal map of the world. And that is when the pace started to feel exponential. Each breakthrough fed the next one. Better compute enabled bigger models. Bigger models produced stronger capabilities. Stronger capabilities attracted more capital, more talent, more infrastructure, and more data. What looked like a sequence of papers was actually the formation of an engine. By the early 2020s, the question was no longer whether AI could achieve astonishing results in specialized research settings. The question was when those capabilities would escape the lab and collide with everyday life. Another subtle change was happening beneath the headlines. The benchmark victories were becoming less important than the transfer. A model trained for one family of tasks could suddenly prove useful for another. Representations learned from text improved code. Representations learned from images improved language grounding. Search combined with learning outperformed hand-tuned heuristics. The field was no longer collecting isolated tools. It was learning how to build generalizable substrates. That is why people inside the labs often sounded more alarmed than people outside them. They were not just seeing smarter demos. They were seeing the ingredients of a system that could keep absorbing new abilities without changing its basic nature. Once that kind of substrate exists, every incremental gain matters twice. First in the immediate task, and then again in all the downstream tasks it unexpectedly unlocks. The consumer detonation. Even after all of that, most of the world still had not fully understood what was happening. Researchers could see the curve. Engineers could feel the change. Investors could sense the coming platform shift. But ordinary people had not yet encountered an AI system that made the new era emotionally real. Then came ChatGPT. When OpenAI released ChatGPT in November 2022 as a research preview, the decisive breakthrough was not only technical. It was experiential. Billions of people already knew how to chat. They did not need to learn command lines, APIs, or machine learning terminology. They could simply type a question in natural language and watch the machine answer in fluent prose. In that single interface, decades of research became legible to the public. The machine was no longer hidden behind enterprise software, recommendation systems, or academic papers. It was speaking directly to people. And once people felt that for themselves, the concept of AI changed almost overnight. It stopped sounding like a distant research topic and started feeling like a personal technology. OpenAI later reported that by July 2025, ChatGPT had more than 700 million weekly users. That kind of scale matters because adoption changes perception. A laboratory success can be dismissed as niche. A tool used by hundreds of millions becomes part of culture, education, work, and politics. Suddenly students were using AI to study. Writers were using it to brainstorm. Programmers were using it to draft and debug code. Customer support teams, marketers, consultants, and researchers were all experimenting at once. The applications were messy, uneven, and often overhyped, but they were real. And once one company demonstrated that conversational AI could capture the public imagination, every major technology firm had to respond. The AI race accelerated because the market now had proof that language models were not just research artifacts. They were products. But ChatGPT also revealed something deeper. It exposed the unsettling breadth of foundation models. A single system could translate, summarize, explain, imitate styles, generate outlines, rewrite tone, answer questions, and serve as a rough assistant across dozens of domains. It was not perfect in any of them, and hallucinations remained a serious limitation, but the range itself was the story. People had grown used to software that did one thing. Now they were facing software that could do many things passably well and some things startlingly well. That changed business strategy everywhere. The old software world was built around menus and workflows designed in advance by humans. The new world suggested that language itself could become an interface layer over knowledge work. If a model can understand intent in plain English, then many tasks that once required specialized software training become conversational. And once that happens, the bottleneck shifts from using software to deciding what you want done. That is why the consumer detonation of AI was not merely a popularity event. It was the moment the broader economy realized that a general cognitive layer might sit on top of existing digital systems. After that, the race was no longer about building a better chatbot. It was about building the first truly useful machine collaborator. And the psychological effect was perhaps even larger than the economic one. For the first time, millions of people had the eerie experience of conversing with a machine that seemed to understand tone, context, and intent. Even when the system was wrong, it was wrong in fluent language. That made its failures feel strangely human and its successes feel almost supernatural. The result was a cultural split screen. Some people saw a toy. Some saw an assistant. Some saw the birth of AGI. But nearly everyone saw enough to realize that the boundary between human-only tasks and machine-possible tasks had moved. In practical terms, that was the moment AI stopped competing only for research prestige and started competing for attention, workflow, and habit. From reasoning to agency. But even the chatbot era may turn out to be only the middle act. The next evolution is that AI is no longer being designed merely to answer. It is being designed to think longer, use tools, execute steps, and accomplish goals. In September 2024, OpenAI introduced its O1 series as models designed to spend more time thinking before they respond, with stronger performance on harder problems in science, coding, and mathematics. That wording sounds modest, but it marks a major conceptual shift. It means frontier systems are increasingly optimized not just for fluent output, but for deliberate reasoning. The point is no longer to sound intelligent. The point is to do more of the cognitive work that intelligence requires. At the same time, labs moved beyond pure conversation into agency. OpenAI introduced deep research in 2025 as an agentic capability in ChatGPT that conducts multi-step research on the internet for complex tasks. Anthropic introduced computer use for Claude, describing a model that can look at a screen, move a cursor, click, and type in the same way a person does. These systems remain imperfect, and companies openly acknowledge important limitations, but the pattern is unmistakable. Models are being connected to tools, browsers, memory, workflows, and environments. Instead of producing one answer and stopping, they are beginning to operate in loops: observe, decide, act, check, revise, continue. That loop is the seed of agency. And agency changes the stakes because a system that can act is economically and socially different from a system that can merely advise. A chatbot can save you time. An agent can restructure labor. Once an AI system can search for information, compare sources, open applications, generate files, revise its own work, and hand back a completed result, the unit of competition stops being the sentence and starts becoming the task. That is why modern AI development increasingly resembles the construction of digital workers. Not flawless workers, not autonomous executives, not magical beings, but systems that can own larger chunks of a workflow than earlier software ever could. And the evolution does not stop in purely digital space. Google DeepMind's Gemini robotics work extends multimodal reasoning into embodied systems, aiming to let robots perceive, reason, use tools, and carry out complex tasks in the physical world. That matters because intelligence becomes far more consequential when it leaves the screen. A model that can reason about text changes office work. A model that can reason about objects, motion, and action begins to change logistics, manufacturing, labs, and homes. The historical boundary between software and robotics starts to weaken. This is also why benchmarks alone can be misleading. The important question is not whether one model scores higher on some leaderboard this month. It is whether the systems are acquiring the components of general problem solving, reasoning, tool use, memory, planning, adaptation, and multimodal grounding. And on that question, the answer is clearly yes. We are watching a migration from predictive text engines to systems that can formulate plans and carry them out across multiple steps. That does not mean AGI has arrived. It means the architecture of everyday software is changing around the assumption that machine cognition can be embedded directly into action. When that assumption becomes normal, the economy does not just get a smarter interface. It gets a new kind of actor. The speed of this shift is easy to underestimate because each product announcement can sound incremental on its own. A model reasons a bit better. A browser tool gets added. A coding assistant becomes more autonomous. A research tool can now synthesize sources instead of only retrieving them. But taken together, those changes amount to a transformation in posture. The model is no longer sitting outside the workflow waiting for questions. It is moving inside the workflow and beginning to share initiative. That is the threshold many people have been waiting for, because once software can share initiative, organizations start redesigning around it. And that is why the phrase artificial intelligence is starting to feel incomplete. What is evolving now is not just intelligence as output. It is intelligence as process. It reasons, chooses tools, interacts with environments, and learns how to complete objectives under constraints. The closer those loops get to reliable performance, the less this feels like search with better wording and the more it feels like the first draft of machine autonomy. When AI starts doing science. If the consumer story made AI visible, the science story may prove even more important. One of the deepest assumptions in modern civilization is that discovery is a human frontier. We expect machines to help us measure, simulate, and calculate, but the act of forming useful hypotheses still feels intensely human. That assumption is now being challenged. In 2021, the Nature paper on AlphaFold described a computational method capable of predicting protein structures to near experimental accuracy in a majority of cases. DeepMind later stated that AlphaFold had predicted more than 200 million protein structures, and the AlphaFold database now provides open access to over 200 million predictions. In 2024, the Nobel Prize in Chemistry was awarded in part to Demis Hassabis and John Jumper for this work. That alone should reset the conversation. A field-defining scientific prize recognized a system that compressed what had been a decades-long biological bottleneck. This was not AI writing marketing copy. This was AI changing the tempo of science. And AlphaFold is not the only example. In 2023, DeepMind reported that its GNOME system found 2.2 million new crystal structures, including about 381,000 stable materials, dramatically expanding the space of candidates for future technologies. In 2025 and 2026, Google described Co-Scientist as a multi-agent AI collaborator built with Gemini to help researchers generate novel hypotheses and research proposals, and the Nature paper presented it as a system for structured scientific thinking and hypothesis generation. The point here is not that AI has replaced scientists. It has not. Experiments still have to be designed, executed, validated, criticized, replicated, and interpreted by humans. But the frontier is shifting. A system that can compress search spaces, propose directions, surface hidden patterns, and help researchers explore possibilities faster is not simply another tool. It is an amplifier of the discovery process itself. And once AI becomes an amplifier for science, the implications spill into everything else: medicine, materials, energy, agriculture, chemistry, and climate technology. In earlier eras, societies became powerful by controlling land, labor, capital, or information. In the next era, a decisive advantage may come from accelerating the speed at which new knowledge is generated and tested. That is why the scientific evolution of AI may matter even more than the consumer one. A chatbot can change habits. A scientific collaborator can change the frontier of what civilization is able to learn. There is also a psychological reason this feels so consequential. When AI helps answer questions, we still imagine ourselves as the true source of insight and the machine as a convenient assistant. When AI begins helping generate hypotheses, invent candidates, or uncover structures that humans can then verify, the relationship changes. The machine starts participating in one of the activities we once thought defined human intellectual prestige. That does not diminish human science. It raises the possibility that the scientific method itself is becoming more computationally accelerated than any previous generation was prepared for. And if the clock speed of discovery rises, history may start moving faster in response. For centuries, progress depended on how quickly trained human minds could read the literature, imagine possibilities, and narrow enormous spaces of uncertainty. Now some of that narrowing can be delegated. The result is not automated truth. It is accelerated exploration. And in domains where the search space is vast, accelerated exploration can be revolutionary. That is why the future of AI may not be defined only by what it says to consumers, but by what it helps civilization discover behind the scenes. Why we are not ready. And that brings us to the most uncomfortable part of the story. We are not just building better software. We may be building a new general-purpose layer of cognition before we have decided how society should absorb it. The economic consequences alone are enormous. The IMF has warned that AI could affect almost 40% of jobs worldwide and about 60% in advanced economies. The ILO's 2025 update found that 1 in 4 jobs globally is exposed to generative AI to some degree, and that the dominant impact is more likely to be transformation of tasks than immediate full automation, with clerical work especially exposed. That means the future of work is unlikely to be a simple movie scenario where every worker is replaced overnight. It is more destabilizing than that. Tasks will be unbundled. Entry-level roles may shrink. Expectations for productivity may surge. Some occupations will be augmented, some compressed, and some hollowed out from the middle. At the same time, the physical demands of AI are growing. The International Energy Agency projects that global electricity consumption by data centers could roughly double to around 945 terawatt-hours by 2030, with data center electricity consumption growing around 15% per year from 2024 to 2030. In other words, the intelligence boom is also an infrastructure boom, with consequences for grids, chips, capital, water, and geopolitics. And while the systems scale, governance is racing to keep up. The European Union's AI Act entered into force on August 1, 2024 and becomes fully applicable on August 2, 2026 with some exceptions. NIST's AI risk management framework was created to help organizations manage risks to individuals, organizations, and society. OpenAI has updated a preparedness framework for frontier capabilities that could create severe harm. Google DeepMind has introduced and strengthened a frontier safety framework aimed at detecting and mitigating severe risks from powerful model capabilities. Even the companies building the most advanced systems are now openly saying, in policy language, that the pace of capability requires serious safeguards. That is revealing. When the people closest to the technology start publishing preparedness and frontier safety frameworks, they are telling you that this is no longer a normal product cycle. It is a threshold. And thresholds are dangerous when societies mistake them for upgrades. So are we ready? Not really. We are experimenting with educational systems that do not yet know what original work looks like in the age of generative assistance. We are experimenting with labor markets that may reward capital and top talent far faster than institutions can protect displaced workers. We are experimenting with legal systems that still struggle to define accountability when an autonomous model takes action. And we are experimenting with geopolitical competition in a technology stack that may shape military power, economic output, and scientific advantage all at once. That does not mean the evolution of AI should be feared and halted. It means it should be understood with adult seriousness. Because this may become the most important technological story in human history. Not because machines suddenly woke up, and not because every wild prediction will come true, but because intelligence itself is becoming industrialized. And once thinking becomes a scalable resource, everything built on scarce human cognition begins to reorganize. The insane evolution of artificial intelligence is not simply that our tools are getting smarter. It is that they are beginning to enter the arena where societies make decisions, create knowledge, organize labor, and shape the future. And if we are not ready for that, the next chapters of this story will be written faster than we can comfortably read them.